Hello, good morning everyone, good morning. Good morning everyone. So I think we have completed the basics of heat engine. From there only we shall start now. Okay, we have completed basics of heat engine. Okay, so from there only we shall start. Okay, then we will derive the Carnot, we will explain, we will talk about Carnot cycle, Carnot's engine and all those things. Okay, so just to get back to what we have studied in the last class, that is heat engine. It absorbs heat, correct? Where source temperature is T1. Where source temperature is T1, it absorbs heat Q1 from the source. The working substance is here, the substance is here, maybe ideal gas or something. It does some work, mechanical work has been done, and that can be seen. Mechanical work done is given as an output, and some heat is rejected out to the sink. So this is a source where it's an infinite source of heat energy. A part of heat energy, say the Q1 amount of heat energy is absorbed from the source, does the work on either expanding or compressing the gas. Work can be done by absorbing this much of heat. The other amount of heat is rejected out to the sink. So now work done W is the amount of heat energy difference. Q1 is absorbed heat, Q2 is rejected heat. Adra naduvid energy that has been used to do work. This is a work done, correct? This is what we have studied. Efficiency is work done by heat absorbed. So it is Q1 minus Q2 divided by Q1, or efficiency is 1 minus Q2 by Q1. Q2 by Q1. Clear? ಇದು ಇಷ್ಟು ಓದಿದ್ದೇವೆ ನಾವು. Next, by looking at all these things, it is quite impossible to have an engine which is 100% efficient. For that, what should happen is, see, this Q2 should be, that is, sink temperature should be maintained. So this is a heat rejected, no? It should not reject any heat out to the sink. So all the heat energy absorbed by the source should be used to do the work. That is why it is impossible to have such an engine which will do the work of 100% efficiency. Okay, 100% efficiency, which is very difficult to find such an engine. Okay, so this is what the outcome was from the heat engine. Then people tried to think about the reversibility of the engines, or if I can, some people, for example, scientist called Carnot tries to reverse a heat engine, or try to get the loop of a heat engine so that it comes back to its initial state. So here There might be compression or expansion taking place, no? Okay, compression or expansion taking place of the working substance. As it absorbs heat, it might expand, correct? Or as it releases more heat, it might compress. But some mechanical work will be done in moving the piston. Hope all of you understand, in moving the piston. Some amount of work is done. Piston is gas compress piston move gas expand automatically due to that expansion piston will come in the opposite direction. It will come in the opposite direction. Is that clear? So that is how mechanical work is correlated. Okay? So this is efficiency of the heat engineering formula. Now Carnot, many people thought it is impossible to have 100% efficiency. But suddenly Carnot gets an idea. If there cannot be any loss of heat, listen to me carefully. If there cannot be any loss of heat, or if the process can be cyclic, that means you start from a point A, you undergo different processes and you come back to same point A, then there will be absolutely no change in internal energy. There will be absolutely no change in its internal energy. Hope you are getting this. Okay, so you start from A, then you end up back to A. Maybe different processes, isobaric, isoporic, whatever it is, without losing the heat, and you are trying to reverse the process. So not to lose the heat is, there should be slower transformation. Okay. Not to lose heat to the surrounding, there should be relatively slow process, not a sudden change. There should be relatively a slow process. Okay. Not to lose heat to the surrounding, the transformation or the change in the process should be relatively slow. Change in the process should be relatively slow. Is that clear? It should be relatively slow. Okay. So such a relatively slow process we call it as quasi-static process. Such a relatively slow change that is occurring where the heat energy of the system and the surrounding is almost same. Almost same means it cannot lose heat to the surrounding. That is the meaning. Some imaginary concept, but yet you have to try to understand this. So not to lose heat to the surrounding, and the changes are very slowly taking place, then you don't observe that changes to be sudden, then there is less chance of losing heat energy. There is much more chance of conservation of heat energy. That is the reason. Is that okay? There is a much more chance of conservation of heat energy. So not to lose heat to the surrounding. So the process should be slow then. Such a process we call it as quasi-static. And he thought of the reversible or cyclic process. Reversible or cyclic process he thought of. So these are the two things that came into Carnot's mind. Then how Carnot's cycle can be indicated? The Carnot's cycle can be indicated using what we call the indicator diagram. The indicator diagram, or it is also famously called indicator diagram. It is also famously called PV diagram. That is variation of pressure and volume in a thermodynamical process. They are indicated. Pressure in y-axis, volume in the x-axis indicates PV diagram. So if the process is isothermal, then there is a slow change like this. Okay? Suddenly this area under the curve gives the work done. Area under the curve, PV curve, gives the work done. Okay? Area under the PV curve gives the work done. Suppose you cycle the process, recycle it, you try to increase the volume to this bit, then you go by adiabatic compression, then this enclosed area enclosed by PV curve, area enclosed by PV curve gives the work done. Area enclosed by PV curve gives the work done. Okay. Gives the work done. Is that clear? Area enclosed by the PV curve gives the work done. Hope all of you understand this. Okay? Idu one point. So, what Carnot thought about? He wanted a relatively slow process. Also, he wanted conservation of heat. But if you don't change the temperature, heat will be conserved. Correct? Temperature is the amount of hotness or coldness of a body. That means it is the average amount of heat energy contained in a body. However, if the temperature is, listen to me carefully, if the temperature is not changed, then there may not be any thermodynamical processes taking place. Correct? Volume may not change. By only changing the pressure, you may not change the volume. By means it may not be that satisfactory. Or moreover, by changing the pressure, you can cause the change in volume. However, by not changing the temperature, there may not be any heat transfer for the processes to follow. So thermodynamic means there should be heat flow from one part of the system to another part of the system, so that due to that heat flow, volume, pressure, everything can change, and due to that heat flow, since the pressure and volume and internal energy whatever changes, there will be some mechanical work done by the engine. Correct? So always you can conserve heat energy by not changing its temperature, by not letting the temperature change. Correct? That you can do. But if you don't let the temperature change, there may not be useful mechanical work. There may not be useful mechanical work. So it is a bit of a challenge now. You have to have an engine which should not lose heat energy, because Carnot is trying to achieve 100% efficiency. Okay? So heat energy should always be conserved. Then the process should be slow so that heat energy can be conserved. However, in conserving the heat energy, if you can't change the temperature, there may not be heat flow from one part of the system to other. From one part of the system to other. Is that clear? From one part of the system to other. That is the reason why it is always challenging to design a 100% efficient engine. So what Carnot thought is, then let me not change the temperature by many stages. I will only change the temperature for 2 stages. I will work the system I will work the system. Okay, I will work the system only between two temperatures. By the way, heading is Carnot's cycle. Okay, here it is Carnot's cycle. Okay, so Carnot's cycle. Is heat engine not written is visible? Okay, clear I know. Now, so what does he try? Carnot's cycle. Okay, it's not visible now. So Carnot thought about this much. Then what he thought was a simple design where he didn't want to lose any heat energy. So he tried 4 processes. This is a PV diagram. First process was isothermal expansion. Isothermal expansion. Is it visible now? Isothermal expansion, where pressure decreases slightly as the volume increases. Where the pressure decreases as the volume increases. So you start from point A, where in point A you have the pressure P1, volume V1, temperature T1. Temperature T1. So that is P1, V1, T1. Is that clear? Next it should go to point B, where pressure is P2, V2 and T1 only, because it is an isothermal expansion taking place. So isothermal expansion means pressure and volume can change at constant temperature. So whatever the initial temperature, that will be maintained again here. Then this is the first process. Second process is adiabatic expansion. Adiabatic expansion. So adiabatic expansion. So this is C. So this is P3, V3, T2 now. This is the second process of adiabatic expansion. So the volume increases again, but without the heat energy being exchanged to the surrounding. Because of the change in pressure and volume, temperature within the system changes, but heat energy is not given out to the surrounding. Okay? Here, if the temperature does not change, however, heat energy is not given out to the surrounding. Again here the same thing. Is that clear? Is that clear? Next, at the same temperature, the third step he prefers is the reverse of this. 2 steps he thought. Okay, for the change in temperature, in order to have the efficient mechanical work, but without losing heat energy, he had to go for adiabatic expansion. He had to go for adiabatic expansion. Not to lose any heat energy, to maintain a constant temperature, he had to think of isothermal process. Now 2 expansions are done. Now the reverse, because I want a cyclic process, so that I am trying to get 100% efficiency of the engine. I am trying to get 100% efficiency of the engine. So what happens? The third process is isothermal compression. Isothermal compression is the third process. Isothermal compression. So this is how it is. Next D. Next I'll have to see expansion. Now see, this is going one direction, this is going in the opposite direction. So I'm trying to come back to its original state, and this one is the fourth stage. The fourth process is adiabatic compression. So ಇಲ್ಲಿ ಏನಾಗುತ್ತೆ, ಇಲ್ಲಿ isothermal expansion ಆಗುವಾಗ pressure will be T4, V4, T2 it will remain. Then as it compresses back to the original volume, adiabatic compression it will be. Adiabatic compression it will be. ಅರ್ಥ ಆಗ್ತಾ ಉಂಟು ಇದು? ಕ್ಲಿಯರಾ? Adiabatic compression it will be. ಕ್ಲಿಯರ್? ಅರ್ಥ ಆಗ್ತಾ ಉಂಟಾ? ಒಮ್ಮೆ ನೋಡಿ ಮಕ್ಕಳೆಲ್ಲರೂ, ಒಮ್ಮೆ ನೋಡಿ ಏನು ಕೆಲಸ ಮಾಡ್ತಾನೆ ಕಾನ್ವರ್ಟರ್, ಎಂತಕ್ಕೆ ಹೊರಟ? he tries to design a 100% efficient engine. ಆಗ ಸಡನ್ ತಲೆಗೆ ಏನು ಹೋಗ್ತದೆ? ಹೀಟ್ ಎನರ್ಜಿ ಎಲ್ಲಿಯೂ ಲಾಸ್ ಆಗಬಾರ್ದು, ಹೌದಾ? ಹೀಟ್ ಎನರ್ಜಿ ಲಾಸ್ ಆಗಬಾರ್ದು. ಐಸೋಥರ್ಮಲ್ ಪ್ರೋಸೆಸ್ ಅಲ್ಲಿ ಸಹ ಟೆಂಪರೇಚರ್ ಆಲ್ಮೋಸ್ಟ್ ಸೇಮ್ ಇರೋದ್ರಿಂದ ಹೀಟ್ ಎನರ್ಜಿ ಲಾಸ್ ಆಗುವುದಿಲ್ಲ. ಪ್ರೆಷರ್ ಜಾಸ್ತಿ ಮಾಡಿದ್ರೆ ವಾಲ್ಯೂಮ್ ಕಡಿಮೆ ಆಗ್ತದೆ, ವಾಲ್ಯೂಮ್ ಕಡಿಮೆ ಆಗಬೇಕು ಅಂದಿದ್ರೆ ಪ್ರೆಷರ್ ಜಾಸ್ತಿ ಮಾಡಬೇಕು, ಆ ಥರ. ಸೊ ಐಸೋಥರ್ಮಲ್ ಪ್ರೋಸೆಸ್ ಅಲ್ಲಿ ಸಹ ಹಾಗೆ. ಕ್ಲಿಯರಾ? ಓಕೆ. ಸೊ ಐಸೋಥರ್ಮಲ್ ಪ್ರೋಸೆಸ್ ಅಲ್ಲಿ ಆ ಥರ. ನೆಕ್ಸ್ಟ್ ಐಸೋಥರ್ಮಲ್ ಪ್ರೋಸೆಸ್ ಅಲ್ಲಿ ಏನು ಟೆಂಪರೇಚರ್ ಚೇಂಜ್ ಆಗದೇ ಇರೋದ್ರಿಂದ ಹೀಟ್ ಎನರ್ಜಿ ಲಾಸ್ ಆಗೋದಿಲ್ಲ. ಬಟ್ ಇನ್ ಆರ್ಡರ್ ಟು ಡೂ ದ ಮೆಕ್ಯಾನಿಕಲ್ ವರ್ಕ್, pressure and volume to change, effectively temperature should change in some stage, correct? Heat energy from part of system, one end of the system, should be transferred to other for it to either expand or to compress. But heat energy should not be lost. That is why he prefers adiabatic system. Why adiabatic? It is completely isolated from the surrounding, so that even though the temperature changes, its pressure and volume, even though the temperature changes, it does not exchange any energy and it does not exchange any matter with the surrounding. That is why he thinks of keeping all the heat energy intact. Is that clear? All the heat energy intact. That is the reason. Then what happens? Then what happens is isothermal compression. Isothermal compression he tries to do, because he has already done the expansion. Now he wants to get back to its original state. He wants to get back to the original state. That is the reason why he tries to compress. Isothermal expansion into inner compression. Adiabatic expansion into fourth stage, adiabatic compression. Is that clear? This is how the Carnot engine. Now he tries to get back to his original state. Now we have to see whether it is possible to achieve 100% efficiency for a heat engine. Whether now it is possible to achieve 100% efficiency for a heat engine. Now First process is as we explained. First process, Carnot's cycle involves 4 steps. Carnot's cycle involves 4 steps. What are they? What are the 4 steps involved? What are the 4 steps involved? In a Carnot's cycle, what are the 4 steps involved in a Carnot cycle? First one is isothermal expansion. Isothermal expansion it is. So, what is the work done in an isothermal expansion? Volume changes from V1 to V2, pressure changes from P1 to P2. So, work done. It absorbs heat now to expand. So, it absorbs heat Q1. It absorbs heat Q1. So, that we will write. By absorbing heat Q1, by absorbing heat Q1, the work done in an isothermal process. In an isothermal process, work done is equal to, for 1 mole of the gas I will consider, per mole of the gas, so it is RT1 log to the base E, volume changes to V2 from V1. This is the work done. So I will call it as W1. Work done in the isothermal expansion. So this work done is indirectly equal to amount of heat energy absorbed by the source. So by absorbing heat from the source only it can do the work. Correct? Correct? By absorbing the heat only it can do the work. Second is the process is adiabatic expansion. So second process is adiabatic expansion. Yes, you try to write the equation for this now. Fast. Yes, what is the expression? Yes, what is the expression now? For adiabatic expansion. So W2 will be R by gamma minus 1 T1 minus T2. This we have derived. R by gamma minus 1 T1 by T2 is the work done in an adiabatic process. So work done in an adiabatic process, adiabatic expansion or process. So the temperature changes from T1 to T2, where gamma is, as you all know, is a ratio of molar specific heat at constant pressure to molar specific heat at constant volume, where gamma is Cp by Cv, where gamma is Cp by Cv. Similarly, the next step is work done in isothermal expansion, work done during isothermal expansion. Try that. All of you please try that. Next, work done in isothermal compression. Isothermal compression now. Third process is isothermal compression. Third one is isothermal compression. So work done in isothermal compression. So you are changing the volume from W3 baritane. You are changing the volume from V3 to V4. So W3 is RT log to the base E. Final volume is V4 by V3, but compression no. So it is minus RT and this is equal to minus Q2, that is heat rejected. So when gas is compressed, its heat will be rejected out to the sink, where Q2 is a heat rejected. Negative sign indicates it is the amount of heat rejected to the sink. Okay, hope it is clear. Next, the fourth process is obviously adiabatic compression. Adiabatic compression, which states W4, that is work done in an adiabatic compression, is R by gamma minus 1, and the temperature change is from T2 to T1. So it is T2 is the initial temperature. Now T1 is the final temperature for the adiabatic compression. Process is from this point D to A. Process is from D to A graphically. Isothermal compression graphically a process C to D. C to D is the process. Adiabatic expansion is B to C is the process. Isothermal expansion is A to B is the process. Is that clear? So W4 is R by gamma minus 1 into T2 minus T1. Is that clear? Clear to all of you? Okay, so these are the processes and work done in those respective processes. Only heat energy is rejected or given out to the system when it compresses. It absorbs some heat when it expands. During adiabatic process, whether it is expansion or compression, there is absolutely no change in heat energy. So what is the net work done? See, this I can write it as, this W4 I can write it as minus R by gamma minus 1 T1 minus T2, which will be minus W2 also. Correct? You can see it clearly. This is minus W2 also. So the net work done W is W1 plus W2 plus W3 plus W4. So here W4 can be negative of W2. So the net work done remains how much? W1 plus W3 is the amount of work done. As ಇದು ಕ್ಯಾನ್ಸಲ್ ಆಗ್ತದೆ ಹೌದಲ್ಲ, ಅಡಿಯಾಬ್ಯಾಟಿಕ್ ಎಕ್ಸ್ಪಾನ್ಷನ್ ಮತ್ತು ಅಡಿಯಾಬ್ಯಾಟಿಕ್ ಕಂಪ್ರೆಷನ್ ಕ್ಯಾನ್ಸಲ್ ಆಗುತ್ತೆ. W4 is minus W2. So ನಾನು ಇಲ್ಲಿ W4 ಬದಲು minus W2 ಅನ್ನು ಸಬ್ಸ್ಟಿಟ್ಯೂಟ್ ಮಾಡಿದ್ರೆ W2 cancels off. Hope all of you understand. Okay? So now we shall move on to, I hope all of you have taken this down clearly. Please go through this again. Then we will continue from this step first. Once all of you please go through this, then from there we will continue. Any doubts you please message. Okay, here isothermal compression takes place at temperature T2. ಇದನ್ನು RT ಅಂತ ಬರೆದಿದ್ದೆ, ಅದು ನಾರ್ಮಲ್ ಎಕ್ಸ್ಪ್ರೆಷನ್. RT2 ಮಾಡಿ because the temperature is T2. So isothermal compression takes place at temperature T2. RT2. Okay, here. Shall we move on? Okay, now what remains is net work done is equal to W1 plus W3. So net work done is W1 is also equal to Q1 and W3 is equal to minus Q2. So it is Q1 minus Q2. So it is Q1 minus Q2. Okay, sorry. So that is one thing. If you go to directly efficiency of Carnot's cycle to be calculated. Efficiency of the Carnot cycle to be calculated. Efficiency is 1 minus Q2 by Q1. 1 minus Q2 by Q1. So that is efficiency is 1 minus Q2 is RT2 ln अथवा log to the base E V3 by V4 we have written V4 by V3 V4 by V3 divided by RT1 log to the base E log to the base E V2 by V1 V2 by V1. Is that clear? This is the efficiency now. So obviously R and R cancels. So efficiency comes to a point where 1 minus T2 log to the base E V4 minus V3 divided by T1 log to the base E V2 by V1. So this I name as some equation star. Okay. So if I get rid of this cycle, Carnot cycle now. Now, the adiabatic changes occur. See here, for adiabatic process, basic equation yavadu PV to the power gamma is a constant. For adiabatic process. And for an ideal gas, PV is equal to RT, no? So P can be written as RT by V. So if I substitute here, RT by V into V to the power gamma is a constant, then this is R goes to this side, that will become constant by another constant R. T V to the power gamma minus 1. T V to the power gamma minus 1 is a constant. This is another basic equation of adiabatic process. This is another basic equation of adiabatic process. So, for adiabatic expansion, from B to C, temperature T1, volume is V2 to the power gamma minus 1 should be equal to T2 V3 to the power gamma minus 1. So if I take the ratio T2 by T1, then that will be V2 by V3 to the power gamma minus 1. Gamma minus 1. Okay, next that implies, okay, that is one thing. This is some equation. So you please note this equation as double star now. Similarly, for adiabatic compression, the temperature changes from last step, no, that is from your Carnot cycle D to A, correct? Adiabatic compression is the last step. D to A agutte. D to A iruvaga curve alli volume should change from V4 to V1, correct? Sorry, V4 is the initial volume final volume should be V1. Fine. So, temperature final should be T1, volume final should be V1 to the power gamma minus 1, temperature ಇಲ್ಲಿ T2, volume is V4 at D to the power gamma minus 1. So, that implies V1 by V4 to the power gamma minus 1 should be equal to T2 by T1. This is another result. So you compare this 2 stars and 3 stars. What you are going to get? Comparing these two, what you are going to get? What you are going to get is V2 by V3 to the power gamma minus 1 is equal to V1 by V4 to the power gamma minus 1 ಆಗುತ್ತೆ. Gamma minus 1 ಆಗುತ್ತೆ. So you can write V4 by V3 is equal to V1 by V2. V4 by V3. 1 minute. One thing you do here, since this value is negative, ನೀವು Q2 heat rejected ಅನ್ನೋದು, so ಇದನ್ನ V3 by V4 ಮಾಡಿ ಇಲ್ಲಿ ನೆಗೆಟಿವ್ ತಗೊಳ್ಳುವಾಗ, this you do V3 by V4, then 1 minute, then V3 by V4 will be V2 by V1. V4 by V3 will be V2 by V1. So, idishtu rough work adara hindettu. So that implies efficiency of the Carnot's engine is 1 minus T2 by T1. Efficiency of the Carnot's engine is 1 minus T2 by T1. Is that clear? It is T2 by T1 is the expression for efficiency of Carnot's heat engine. Efficiency of Carnot's heat engine. Carnot's heat engine. ಇದು ಇಲ್ಲಿ heat rejected out ಆಗಿರೋದ್ರಿಂದ because of the compression ಇದು ನೆಗೆಟಿವ್ ಆಗುತ್ತೆ. ಸೊ ಅಲ್ಲಿ ಸೆಕೆಂಡ್ ಸ್ಟೆಪ್ ಅಲ್ಲಿ ನೀವು ಬರ್ದಿದ್ದೀರಲ್ಲ, ಅದನ್ನ ಮೈನಸ್ ಮಾಡ್ಕೊಂಡು ಮೈನಸ್ ಸೈನ್ ಒಳಗೆ ತಂದ್ರೆ you can exchange V3 and V4. Correct? That is what I have done. You can exchange V3 and V4. Okay? So that is heat rejected out. No, since V4 is lesser in volume compared to V3. Okay? So Carnot tried his best to design a heat engine. Carnot tried to design a heat engine to give 100% efficiency, but 100% efficiency can only be achieved if the sink is maintained at 0 Kelvin temperature, that is minus 273 degrees Celsius. It is difficult to maintain a heat engine at absolute zero. Okay, at absolute zero. That is the reason why second law of thermodynamics came into effect. There are two statements. So Carnot tried his best to taking all the precautions and thinking about it, but still he failed to Carnot failed to design a heat engine which is 100% efficient. That is why what he has done here is the effort to design a 100% heat engine, but then for the whole world it is understood that it is impossible to design a 100% efficient heat engine. So then came second law of thermodynamics. So naturally heat flows from hotter to cooler region, and not all the heat energy absorbed will be utilized to do the work, to do the mechanical work. Hence, the second law of thermodynamics came into effect. So, there is a second law of thermodynamics which came into effect. Okay. So, the second law of thermodynamics states there are two statements. Second law of thermodynamics states, first statement is Clausius statement. So it states it is impossible to transfer heat from cold body to hot body without any external work. Second statement, that means natural flow of the heat will be from hotter to cooler body only. So if you somehow forcefully can transfer heat from cooler to hotter body, then it is fine. Okay, then it is fine. Next, the second one is Kelvin-Planck statement. Next, the statement is it is impossible to get continuous supply of work by cooling a body to a temperature below the coldest of surroundings. Below the coldest of surroundings. So these are the two statements. It says it is impossible for the heat to flow from cooler to hotter body, and it says it is impossible to get the continuous supply of work by cooling a body to a temperature below the coldest of surroundings. that is the reverse of heat engine, which is called refrigerator. That is called reverse of heat engine. So if you only keep doing the continuous work, then there is a possibility that a temperature from the coldest of the surrounding can be given out to the surrounding from the cooler body. Okay, so these are the two things, and it is also impossible to design a 100% efficient engine. See, this word impossible tells you there cannot be any heat transfer from cold to hotter body without any external work. The same thing is said in another way. You have to supply continuous work to get the body to a temperature below the temperature of the surrounding. For that you require continuous work. Hence it cannot be 100% efficient. So this is actually talks about the action of refrigerator. Refrigerator is a reverse of heat engine. Okay, so that is, for now it is deleted. We will see as and when we come to it. Okay, refrigerator for now is deleted. So we will of course teach you that as and when we come to it. Okay, so this is about the theory of thermodynamics. We shall solve some more problems on this chapter now. Okay. Any doubts you can ask. Now we shall take up some Ncrd problems. Write down the question. In changing the state of the gas, in changing the state of a gas adiabatically from equilibrium state A to another equilibrium state B, an amount of work equal to 22.3 joule done on the system. If the gas is taken from state A to state B, via a process in which the net heat absorbed by the system by the system is 9.35 calories. How much is the net work done by the system in the latter case? Take 1 calorie equal to 4.19 joule. Write down the question fast. So I'll read out the question. In changing the state of a gas adiabatically from equilibrium state A to another equilibrium state B, an amount of work equal to 22.3 joule done on the system. If the gas is taken from state A to state B via a process in which the net heat absorbed by the system is 9.35 calorie, how much is the net work done by the system in the latter case? How much is the work done? Net work done by the system in the latter case. So, see here, this energy 22.3 joule. 22.3 joule is utilized in changing the state. Changing the state means internal energy. So that is how we have to think. So this energy is used to change the state. That means change of state means change in internal energy. So 22.3 joule of work is done. Is that clear? Okay. So net heat supplied is, if the gas is taken from state A to B, process in which net heat absorbed is 9.35 calories into 4.19. That will become around, how much it will become? 39 point something. 39.18 joule. So by first law of thermodynamics, it will be dq is equal to du plus dw. I hope all of you are getting this. Okay. So what happens now? dq you substitute 39.18, du you substitute 22.3, dw we have to calculate. So then dw will be 39.18 minus 22.3. So dw will get 16.88 joule. I'll get 16.88 joule. Is that clear? Okay. Please take down the question fast and answer also. dw is 16.88. Okay, so I'll drop this question. We'll move on to the next question now. Next question. A steam engine delivers 5.4 into 10 to the power 8 joule of work per minute and receives 3.6 into 10 to the power 9 joule of heat per minute from its boiler. What is the efficiency of the engine? How much heat is liberated? How much heat is wasted per minute? How much heat is wasted per minute? How much heat is wasted per minute? I hope the question is visible. A steam engine delivers 5.4 into 10 to the power 8 joule of work per minute and receives so much of heat, 3.6 into 10 to the power 9. What is the efficiency? Efficiency is work done by energy input. So work done is so much of work, 5.4 into 10 to the power 8 divided by it receives how much of energy? This much of energy. That is 3.6 into 10 to the power 9. So if you are smart, 3.6 ones this is 1.5 so 1.5 into 10 to the power minus 1 units. So it is 0.15 is the efficiency. That implies efficiency is 15% only. 15% only. Is that clear? 15% only. Then energy wasted per minute. Energy wasted per minute is energy input minus work done. No, energy input minus work done. So energy input ಎಷ್ಟು 3.6 into 10 to the power 9 minus 5.4 into 10 to the power 8. ಇದನ್ನು ನಾನು 36 minus 5.4 into 10 to the power 8 I can write. Into 10 to the power 8 I can write. That is equal to 36 in the 5 ಹೋದ್ರೆ 31. This is 30.6 into 10 to the power 8 joules of the energy is wasted every minute. Every minute so much of energy is wasted from that steam engine. Is that clear? Understood? Okay? We'll go to one more problem now. One more. Write down. An electric heater supplies heat to a system at the rate of 100 watt at a rate of 100 watt. If the system performs work at a rate of 75 joule per second at what rate internal energy increasing? At what rate is the internal energy? Okay. At what rate internal energy is increasing? Easy one. So that is heat supply per second, everything is per second only. So I'll use the first law of thermodynamics, that is dq is equal to du plus dw. So this is 100. If the system performs a work, so work is done by the system only. Work is done by the system, so the work done should be then positive. So 100 minus 75 is du. 25 joule per second is the rate of increase of the internal energy. So ಎಲ್ಲವರು ವ್ಯಾಟ್ ಅಲ್ಲಿ ಹೇಳಿದ್ದಾರೆ, ಇಲ್ಲಿ ಜೌಲ್ ಪರ್ ಸೆಕೆಂಡ್ ಅಂತ ಕೊಟ್ಟಿದ್ದಾರೆ. ಸೊ ರೇಟ್ ಆಫ್ ಇನ್ಕ್ರೀಸ್ ಆಫ್ ಹೀಟ್ ಎನರ್ಜಿ, internal energy, rate of increase of internal energy is 25 joule per second. 25 joule per second. Is that clear? Okay. Okay, next we shall move on to one more question. Calculate the efficiency of a heat engine working between 100 degrees Celsius and 400 degrees Celsius. If it absorbs 200 joule per cycle from the source, calculate the heat rejected to the sink in one cycle. Calculate the heat rejected to the sink in one cycle. So see, the engine is working between 100 degrees Celsius and 400 degrees Celsius. So the higher temperature should be temperature of the source. Temperature of the source should be the higher one, which is T1, which is 400 plus 273, which is 673 Kelvin. Similarly, temperature of the sink is 100 plus 273 is 373 Kelvin. It is T2. So T2 is 373 Kelvin. Clear? So we have efficiency now. Efficiency of the Carnot engine is 1 minus T2 by T1. Just now we have derived this. So 1 minus T2 is 373 by T1, which is 673. So it will come around 1 minus, what is the answer here? 0.55 I think. So this is 0.45 is the efficiency. Next, heat rejected we have to calculate. So we have to calculate Q2, right? Q2 ಎಷ್ಟು ಅಂತ calculate ಮಾಡಬೇಕು. Comparing two equations, second part ಗೆ ಇದು comparing 1 minus Q2 by Q1 is the efficiency. 1 minus T2 by T1 is the efficiency of the Carnot heat engine. This is the efficiency of any general heat engine. So you can always write Q2 by Q1 is T2 by T1. So I have to calculate Q2 now. That is T2 is how much? T2 is 373 by 673 into Q1. Heat absorbed is 200. So idu 0.55 into 200, which is 110 joule. Heat absorbed, if it is 200 joules, heat rejected is 110 joules to the C. That is the answer. Okay. So this is the efficiency of the heat engine. This is the efficiency of the Carnot engine. Okay. So we have completed most of the problems of this chapter. So in the next class we will try to continue with kinetic theory of gases. Okay. Thank you.